This is Calculus Intro to Implicit Differentiation, and we're going to look at the derivatives derivatives of y with respect to x. So this first problem should seem pretty basic to us. The action to begin with is we're taking the derivative of both sides of this equation with respect to x. So that is our action. The derivative of y with respect to x is this dy dx. On the right-hand side, the outermost function is 3 something to the fifth. So if we take the derivative of this using the power rule, we get 15, that something to the fourth, then times the derivative of the inner, and we have this as our dy dx, the derivative of y with respect to x. Now that's significant as we look at this problem number 2. It's exactly like problem number 1, but instead of this x squared plus 2x being the something, now we have the u being the something. So like the first problem, we're going to take the derivative of both sides with respect to x. The left side is dy over dx, the derivative of y with respect to x. And then on the right-hand side, the outermost function is 3 something to the fifth. So we'll use the power rule on that, 15u to the fourth. But now our inner function is u. And we have to take the derivative of u with respect to x. Just like on the left, when we took the derivative of y with respect to x, we wrote dy dx. So when we take the derivative of u with respect to x, we get du dx, and that's as good as we can do with that one. Number 3, we're going to do a similar type idea here. We're going to take the derivative of everything with respect to x because we're looking for the derivative of y with respect to x. So on the left-hand side, when we take this derivative, it's dy dx. The derivative of x cubed with respect to x is 3x squared. The derivative of 5 is just 0. But then this middle function, the one in yellow, the derivative of 2y squared is 4y, and times that inner function is dy dx. Jack LaManna. Jack, wave, say hello. All right, back to the problem. So then the goal is to find dy dx. We're going to move this yellow term over to the left, so subtract from both sides. And then from red over to the screen, we factored out dy dx, divide by what we have inside of parentheses, and here's the derivative of y with respect to x. And note that this is a function of both x and y, because the function, or this is not actually a function. There are 2 places where x is equal to a lot of different numbers, so we need to know the derivative at x and y values together. Number 4 is the first problem where we're taking the derivative with respect to this variable t, which we'll see a lot in future problems dealing with time. We're taking the derivative of both sides with respect to time. So that is the action. We have to use the product rule on this first part, so it gives us this big mess up front. The other parts, even the derivative of the x squared this time becomes 10x dx dt. The derivative of the 6y is -6 dy dt. And we're trying to solve for dy dt, so like we did before, we're moving all the dy dt's to one side, then factor it out so we can solve for dy dt by itself. Last one is the derivative of arc sine of x. That's what the sine to the -1 means here. It is the sine inverse of x, not 1 over the sine of x. This is equivalent to saying sine of y equals x. So using right triangle SOHCAHTOA, I know what this means. Y is the angle. The sine of our angle y is opposite over hypotenuse. If we use Pythagorean theorem, this side would be square root of 1 minus x squared. So taking this green highlighted equation and taking the derivative of both sides with respect to x, and I know it's with respect to x because of how it's written up here. The derivative of the left side is cosine of y times dy dx. The derivative of x is just 1. To get dy dx by itself, divide both sides by the cosine of y. And then here is an answer. But going back to the drawing, the cosine of y is adjacent over hypotenuse. So I can plug that in for the cosine of y, and there is dy dx.